Hi, this is Paige Roberts, Open Source Relations Manager for Vertica. And I'm going to talk to you today about how to get your machine learning into production faster with in-database machine learning. Now, since financial services and fintech is kind of the focus here, I'm going to talk a lot about how to get your fraud detection, your risk analysis, your security analysis, your anomaly detection, all that sort of thing into production faster with in-database machine learning. So let's launch it. So what I'm going to start with is an introduction, not of me, because you don't care about me. What you care about is, does this actually work? So I'm going to start off with kind of some examples and one good in-depth example from beginning to end, so that you can kind of see the process, see why folks would do this and how it worked and stuff like that in a real world situation. And then I'm going to tackle more of the sort of big ideas of it. So what are the challenges with trying to get your machine learning into operation? Is in-database machine learning really a thing? Does it actually work? If it does work, why would I want to do it? How would it help? And then kind of like, how does that work? What do I need to do to make that happen? And let's go on. I've got questions on there, but I just got told that probably I won't have time for questions since it's pre-recorded. So let's go ahead and see what we got here. So one of the first things I want to talk about is just that this is not a future thing. Machine learning, advanced analytics, time series, geospatial, all of this is it's out in the world now. I mean, Philips is using it, predictive maintenance, IoT analytics to make sure that the MRI machine or the CAT scanner or whatever isn't broken the next time you go to the hospital. You've got Hewlett Packard, HPE over there with their HPE InfoSight capability, making sure that your data centers still work, including the ones that drive cloud business. So, what are you trying to do? What you're trying to accomplish? Well, obviously, you want to do something in the financial services. So I'm going to start with talking a little bit about EOI tech. Now, if you haven't heard of EOI tech, that's because you don't live in China. So we're a global company, and we talk to a lot of different people, and pretty much all the examples I'm going to give you are Vertica examples, mostly because nobody else's customers really want to talk to me. But what that means is you get a very global perspective. You're not just looking at the United States. We have lots of use cases there, but the thing about the United States is the financial services in particular is very closed-mouthed about how they do things. So in China, they're a little bit more open, and so the EOI tech folks can talk to us and can let us talk to you about what they're doing. So what they do is they're actually an analytics company that does all of their analysis for the financial services sector. So they do everything from plain old BI reporting to things like fraud detection and anomaly detection and security and risk analysis. And most importantly, one of the big things they do is try to keep the lights on. They try to do a lot of AI ops so that the networks and the computers and everything that every company, including every financial company, depends on, keeps running and stays solid. So let's look a little more closely at that. So one of the problems that they had when they decided to tackle this big problem of keeping the lights on at all the large Chinese banks, China Union Pay, which is the Chinese version of Visa, all of these companies dependent on continuing to run and to detect cybersecurity intrusions and fraud and things like that were always anomalies. They were always something that was wrong, that was weird. And they had to look through thousands of instances to find the one or two or however many that were not right. So they had to combine a lot of things, everything from transactions to events that happened, performance metrics, application logs. All of this stuff is, every single bit of it is in a different format. None of it is compatible. None of, the date timestamps aren't even compatible. You had to like interpolate even to join it. There's a lot involved in this. Now, since that was that complicated, they mostly just looked at the logs. They used Hadoop and Elasticsearch, which was kind of the old way of doing this. And for many of their customers, this was really bogging them down. It required a lot of time. And the more customers they had, of course, the more this became a problem because it really just didn't scale well. One of the trouble with Spark clusters, Hadoop clusters of any kind, but especially those run with Spark, is they're only designed to have maybe at best 10 concurrent users. Anybody who knows this sort of thing, it's like there's going to be more than 10 people who want to use your fraud detection capabilities, your risk analysis, your cybersecurity intrusion detection. It's like there's a lot more people than 10 that want to look at everything, including your business intelligence on your company, all of that. So they couldn't keep up with their customer demand. So what did they do? Well, they switched to in-database machine learning. Now, what does this give them? Well, for one thing, they use Vertica, so they had got this really nice compression ratio. That's something that we're kind of famous for. And we use it for a couple of things. One, to save storage costs, but also to save processing time. So you get better performance because you're processing on smaller amounts of data. This also let them pull in data streaming as it came, this is a pretty common thing with lots of databases, that you can now pull in data from Kafka or Kinesis or Pulsar or something like that, where the data streams in and you can look at it as it comes in. So you can get very fast response times when you're at the operational stage, when you're at the point where you're trying to predict something or catch something like, oh, look, that's fraud. Boom, I caught it in milliseconds. That's a big win. That means you can prevent it before it actually completes. So one of the big things they got was 80 to 90% speed up. And that accelerated their response times by a factor of 10 and shortened their client troubleshooting time from hours down to minutes for their AI ops. So that when somebody had a problem, they were maybe down a few minutes as opposed to hours. Now, the big things they kind of were surprised by, but was because of that compression ratio, they were also able to use 10 servers per client instead of 50. So that's nice. This is Zalbo Gay, and I hope I am pronouncing Zalbo Gay. I'm hoping I'm pronouncing his name correctly, but probably not. That's my best attempt. So they were using Spark before, and they got an 80% time reduction, because the problem with Spark is it doesn't function until you first read the data off of disk or off of an object storage system. Either way, you have to read it all into memory, and then you can do step 2. In database machine learning, because databases are optimized for read speed, for analytic speed, you're going to get a big acceleration in time, and it also gives you a lot more flexibility. So they were able to pull in those KPIs, pull in a whole lot of other data, and get more information than just logs. This meant that that they could do more, including capacity planning, trend prediction. So they gained a lot from just switching from one technology stack to another. In database machine learning is pretty revolutionary, and a lot of people don't even think that's not even in their brain when they're thinking about how do I do machine learning. So let's talk about machine learning in general. It's like, what's the difficulty? Why isn't everybody doing it? I mean, obviously this really worked out well for EOI Tech and for all of their companies that they serve, all their clients, all the like financial services, big banks, and their version of Visa, and all these people, they're doing a lot better with machine learning. Why isn't everyone doing it? Well, because it's hard. I think that's the obvious answer. Machine learning is not simple, and many of the projects that are started take about 90% of them just never make it into production. So what you have to kind of keep an eye on is how long is it taking you to get production, even for the ones that succeed. I mean, some of these are just experiments, and sure, they're going to fail because you're going to go, hey, that's not a good model, I'm not going to use that. But a lot of the problem is time. So I had a dinner not too long ago with a bunch of CDOs and CDAOs and directors of analytics, and I had two ladies who were sitting side by side from two different companies, and they were both directors of analytics. And I asked the first lady, I said, so how long does it take you to get from I have an idea of how I can use machine learning to improve my business to that idea is now in production? It's saving my company money. It's catching fraud. It's doing what it's supposed to do. How long, what's that time gap? And her answer was, well, 3 weeks. We're working on it. We're going to get faster than that. And I was quite stunned, as of course was the next lady that I asked, because she said 6 months to a year if we're lucky. And that is the problem. Which one of those do you think was using machine learning inside a database? That's the deal. That's the big difference. So right now, even of the models that get into production, a lot of them are taking 3 months, 6 months, a year, even longer to get into production. And that's insane. That is just not useful to most companies. Why? Why is that a problem? Where is the workflow getting stopped? And the answer is almost always, this is one survey. I've seen half a dozen surveys that all say the same thing. It is getting stopped at the proof of concept stage. Our data scientists are doing their jobs. They're proving out a machine learning model and saying, this is a good model, put it into production. And then they're tossing it over the wall, and it's taken 3, 6 months, a year or more to get into production. Why is that? Well, the main reason is because the development environment and the production environment are completely different. It's like, this is totally new stacks. It's like, on one hand, we're doing interactive stuff on a notebook. We're training things. We're probably doing it in batch. We're grabbing a whole bunch of stuff and just putting it there. We're using little samples, whatever will fit in memory on our sandbox or on our computers. And we're just, doing that. We're just one person or maybe a little team, 2 or 3 people. We don't have to worry about managing resources. It's like, there's only one, you don't have to manage a one. That's a pretty easy one. So when that model is done, they throw it over to the production environment. It has to be completely redone for production. And there's no notebook. It's all automated. It's all predicting on real-time data that's streaming in. There's lots of nodes. It's got to scale out. It's got to use old data. It's got to look at the full data set, which could be gigantic. So if you did 30 steps to get your data ready when you were doing your experiment, then somebody's got to reproduce all 30 steps in the pipeline leading up to the inference. And of course, there are concurrent jobs. While you are trying to infer, you've got your boss over there also trying to, look at his BI dashboard. It's like, you can't slow that down while you're trying to do this. It's like, these two things cannot bump into each other. There can't be a contention. And if I have 100 people and all of them are doing something. Maybe some of them are watching for fraud. Some of them are, which maybe that's automated, and so instead of 20 people, we have 200 automated processes all at once. This is a problem. Concurrency is a big deal. All right. So right now, we're pulling data out of wherever it is. Maybe it's a database. Maybe it's sitting on a public data set on a cloud. Maybe it's some files on somebody's system. We're pulling all this data, but we're not pulling all of it. We're just pulling a sample. And we might have to do that 2 or 3 times to try and get something that covers, the gamut that's statistically significant. But this is going to be especially a problem if we're trying to detect anomalies, because of course there might be 100 normal things before we get one fraudulent transaction, one cybersecurity intrusion, one thing that's different. It's like, and if you're just pulling out a sample, it's really hard to get those. So that is a difficulty, but it also causes a reduction in your accuracy, because everybody knows that in machine learning, more data, more good data, of course, beats even a better algorithm. So you lose some accuracy and a lot of time trying to pull everything over there. So then you do your data preparation, you train your model, you evaluate it, you're like, okay, this is good. That takes a little time. But then you got to give it to somebody else, and they got to rebuild it in something else like Spark. Something that scales, something that's distributed, something that can handle your entire data set. And that could take months. Somebody's got to rebuild everything you did at scale. And the other problem is, over time, the data drifts. So what might have been a super accurate model when you tested it and developed it might be far less accurate, even to the point where it's not even useful by the time you get it to the end of that process. So this is the process we got to fix. All right. What are the problems? Well, it costs a lot. Your stacks are huge. Trying to maintain all of that, even if you're doing it all open source, all your software is free. That just means you got to pay people with expensive skills who know how to use each individual piece, and you've got to maintain it all. It's like if I upgrade one thing and it throws everything off, and now none of my code works, that's a problem. You've got to be really careful with your maintenance. It requires downsampling, which affects your accuracy and reduces, increases your time to development, which of course is going to take a lot of time, because it always does. That's actually not that different for database machine learning versus any other kind of machine learning. But once you've developed it, then you've got to deploy it, and that takes a lot of time. And this is where database machine learning really shines. So what does it look like if I do all of this inside a database? Well, first, I start out with a database. So I'm putting all my data in the database. Now, you're like, well, databases only do structured data. That's only rows and columns. Well, most algorithms only do structured data too. What you need to do is put your data in there that's semi-structured, that's that you have to define the structure after you get it, that schema on read, all that kind of stuff. It's like you've got to be able to query data that isn't even in the database format. Maybe it's sitting in Parquet on object storage system. Most databases nowadays, your modern analytical databases, can do everything I just said. This is not your data warehouse from 30 years ago that could only do one thing, only row and column, period. That's it. But what it can do for you now is it can do a lot of the data prep for you, because it can pull in data from all of those different forms and put it into the row and column format that your algorithms need. So that makes life a lot easier. You can do a lot of the data prep already inside your database, and then you can save your intermediate data set, and that means other people can use that data set. And that's very handy if you have a team of data scientists working on it. It's also really handy if you need some reproducibility, because you saved your data set. You can go back and retrain on that exact same data set and see which features influence things and stuff like that. So another thing is that a lot of things like impute missing values and normalize your data set and all that kind of stuff is in that database. It's already in there as functions. So you don't have to pull it out and go do it in some other package. It's already in there. But the interface is either SQL, sure. I mean, if you're comfortable using SQL, you can train a regression classifier. You can check it out your model with a ROC curve. You can do all of that with SQL, but most folks would prefer to do it, say, in a Jupyter notebook using something that looks like Python code, or they'd prefer it using R as their interface. And almost everyone has some secret sauce, some special, unique thing that they need to do. And most databases let you do a unique thing, like, let me build this special function in Python. We had an example, Jaguar Racing. They needed a special low-pass filter just for their Formula E race cars. It's like nobody else needs that. That is something unique to them. They built it. They put it in the database. It acts like just one of the functions. It gets distributed, which means it gets all of that nice parallel processing, and it works really quickly. And that's the only thing they had to build. They don't have to build all the rest of it because it's already there. So that is pretty much the idea behind in-database machine learning. You end up vastly reducing your amount of time, not losing any of your accuracy, and getting things into production in minutes, not months. All right. So that all sounds really awesome. Yeah, but is it real? And the answer is yes. There right now are a bunch of analytical databases out there that support in-database machine learning. In fact, most of your good analytical databases, I'm not talking about stuff that's designed for just transactions. I'm talking about all the databases like Amazon Redshift has SageMaker, it has Athena, it can query all kinds of things, it can do machine learning, Google BigQuery has Google ML. Those are Vertica just has it all in one package. These things exist and it is out there. And it includes the full set of functions. It's like, oh, well, am I going to have to do my feature correlation beforehand? No, it's in there. Well, what if my, data set isn't normal? What if I have to normalize? Oh, you can do that. What if I want to, like, I don't know, test for heterodiscity? It's like, that's totally in there. What if I want to join not just regular old data? What if I want to take some time series data from two different places and put it together, even though the date timestamps aren't quite right? And there's all these, if I set it up, there's going to be all of these missing values I'm going to have to interpolate. Can I do that? Yes, you can. Can I put two geospatial area things together so I can tell if my house is in a floodplain, or if here's the area of effect of one telecom tower and here's the area of effect of another? I need to be able to tell, does this guy over here, does he have cell reception? Yes, I can do that. I can also train with all of my common models, my classifiers, my regression models, my random forest models, my tree models. All of that is built into most analytical databases, or it's an add-on that you pay for. Either way, you've got in-database machine learning. And that includes the end-to-end process. We're not talking about just training your algorithms, which is what everybody goes to as soon as they hear the word machine learning. They're like, well, yeah, but do you have support vector machines? Which is like, can I do principal component analysis? It's like, yes, you can. But that's not where you start. You start with pulling in all this data, and you pull it in streaming from Kafka. You do SQL queries to your transactional databases. You pull it off your HDFS or your S3 or your Google Cloud or wherever. You pull in semi-structured data, which we call Flex, and then you do your SQL on read. You want to query data in place like your Parquet data, but it's hierarchical. It's really complex. You have to be able to do all of that in order to first explore the data that you have, summarize it, find the outliers, do all the things that you need to get that data ready, like your joins and your normalization and filtering. When I say sampling, I usually just mean splitting, test, and validation. There really isn't any good reason to reduce your data set other than maybe, hey, maybe you want to balance out. I have, this many anomalies and this many real things, and that helps train my model. You can do that. You can evaluate your model. You can deploy your model right next to your data set. You can use the interface that makes you happy, SQL, Python, R. We have a Vertica Pi interface that's a mix of Python and Jupyter. And your database is actually doing all the work. So the fact that you're writing R doesn't mean you have to limit yourself to a data size or that R can handle, because you're really just telling the database using something you're used to do a procedure on a large amount of data. And you can import and export your models using PMML. You can store them in the database. You can go train your TensorFlow models on GPUs, but you don't want your production stuff on GPUs because that's expensive. You can pull in your frozen graph and put it to work in your database. So that gives you kind of an idea. I mean, nowadays, even the data that the database stores, ROS is our own internal format. Every database has their own internal format that they save things in. And it's usually really, really optimized for read and analyze. But the thing is, they're saving it in S3 buckets. It's like that data is sitting right next to the Parquet and Oric and JSON and CSV and all this other data. And most of your databases can now query that. Or they'll have an add-on like Athena for Redshift, where you pay extra and now you can query all of that. This is the power of a modern database. So you want to be able to have that. But what is it going to give you? Well, it's going to eliminate that overhead of data transfer. You don't have to move your data out of your database, put it back in your database, make sure you have the right sample, all of that. And that increases your accuracy as well, because you're using as much of the data as makes sense for your algorithm. Your data security and provenance is going to be way better. And this is hugely important when you're dealing with people's financial data. Your databases are mature. Their security, their governance, all of those things that are built in and have 30 years of maturity behind them. So your data is genuinely secure. And instead of moving it around from stack to stack to stack, it's staying in one place. That makes your provenance a lot easier. The models are stored right next to the data. You can manage them right there. You can serve as many concurrent users as you want and as many concurrent use cases, as many concurrent jobs. So if I have 200 automated fraud detection things going at once, that can happen. If I'm training a machine learning algorithm over here, you can isolate that so it's not interfering with your boss's dashboards, with an application that's doing fraud detection, with whatever you need. Those things can work simultaneously, and databases nowadays are designed to isolate those workloads so that you never slow down or bog down the entire database just because you're doing one thing. All right. Highly scalable machine learning functionalities. It's all parallelized in there. That engine is powerful. You only have one system to maintain, or at most, a couple more. Let's, Redshift, SageMaker, Athena. That's great. That's 3 things. You're not looking at a whole stack for development and a whole stack for production. You're looking at a thing with Vertica, 3 things with the Amazon stack, 2 things with the Google stack. It's like, this is so much easier to take care of, to keep up to date. And most of all, your database is the same. It's like I'm going to have a development database, a production database, a QA database, maybe a high availability or disaster recovery database. They're all going to be the same. They're all going to be designed the same. They're going to have the same environment. They may not have all of the data depending, on what I need, but it's going to be the same tech, the same environment, and pushing from one to the next takes a simple command. One command, a couple of seconds. So I could get my machine learning model that is done and ready to go into production in minutes, not months. So how does all that work? Well, I'm not really going to dive into this too much, but the simplest thing to explain is a tree classifier, because of course it's going to put different trees on different nodes, and you can do all of this at the same time, and then it comes together and gives you your random forest or your XGBoost or whatever, and you get the general idea of this is going to be a heck of a lot faster than if I'm doing it on one node, if I'm doing it all serial, one thing after another. And what that gives you is not just I get it done faster. Okay, well, that's nice. What it means is that instead of one iteration, instead of 10 iterations, maybe you could do 100. Maybe you could get a more accurate model. Or, maybe you can use your entire data set with the same amount of time and get your accuracy that way. Either way, what it means is not just faster work, more productivity, it also means better machine learning models. So I'm just kind of like, it gives you an idea of all the things or a few of the things. This is like a tiny fraction of some of the things that you can do inside of a lot of different databases. XGBoost, all of your ARMA things, your Surima, your Verima, all of the time series analysis capabilities, and you can integrate with other technologies, because even if you've simplified your stack, you're still going to have a stack. You're still going to have things that you want to work and play well with. And this is one of those things that databases are designed for, is to integrate well with things that are putting data into them and be really good at exporting data, including models. So that makes your life a lot simpler. You've got something that's doing most of the work, but it's really happy to work well with the rest of your stack. Now, we realize that this is something that a lot of people just don't think about, and a lot of people are skeptical of. So Vertica put out a bunch of examples. They're very simple examples using public data sets, using our free version. Vertica has a up to 3 nodes, up to 1 terabyte version that you can just download and use, or you can spin up on your favorite cloud, whatever. And you can just try this out, and you can see this really works. In fact, if you look in your Jupyter notebooks and you start doing this, that's what all these are. They're Jupyter notebooks. It is hard to tell that you are not just building this on a laptop with some, with your standard pandas and scikit-learn libraries. It looks pretty much the same. The big difference is that you can do the exact same thing with 100 terabytes of data. And that is huge. That really gives you an edge. And then when you're done, you can get this into production lickety split. And that is an even bigger edge, because until you get it into production, you don't look like a hero. You just look like a cost center. And that is not what anybody wants. All right. So here's another good example. Cardlytics does loyalty cards for a lot of banking and, mobile banking and things like that. And they also switched from Spark, got better performance, but the big thing that they got was stability, because your database is mature and stable and reliable. That makes also a very big difference. Finance Bank, they did some really cool stuff with cybersecurity. They also are generating reports, just plain old-fashioned BI, and they just discovered that they could do a lot more once they moved to in-database machine learning. In particular, they discovered they could do a lot more simultaneously and with bigger data sets. So they're looking in particular for cyber threats, and this is a nice quote, which I will not read to you because I'm pretty sure you know how to read already. And I'm running low on time. So I did a nice little book with O'Reilly, and it is about accelerating your machine learning with a unified analytics architecture, which is really just a database and a data lake kind of merging together and becoming one, and in-database machine learning to deploy your models in minutes, not months. So be sure and go out and check it out and read it. It's like this thick. It's not one of those giant animal books that you have to like set aside 3 months to get through. This is a really good one that you can breeze through in a couple hours and have the ideas in your brain going forward. So with that, I think I'm done, and I want to thank you guys for coming.